Hey team, thanks for joining me. I'm Corey. I go by coreyja on the internet. You can find me at coreyja.com or coreyja on GitHub, YouTube, and Twitch. Today we're going to do an Advent of Code puzzle. Advent of Code is these programming puzzles that come out every December from the 1st to the 25th. And we are on day 11. So let's get right into it. Day 11, Cosmic Expansion. You continue following signs for hot springs and eventually come across an observatory. The elf within turns out to be a researcher studying cosmic expansion using the giant telescope here. He doesn't know anything about the missing machine parts. He's only visiting for this research project. However, he confirms that the hot springs are the next closest area likely to have people. He'll even take you straight there once he's done with today's observation analysis. Maybe you can help him with the analysis to speed things up. The researcher has collected a bunch of data and compiled the data into a single giant image, your puzzle input. The image includes empty space and galaxies. For example, something like this. The researcher is trying to figure out the sum of the lengths of the shortest path between every pair of galaxies. However, there's a catch. The universe expanded in the time it took the light from these galaxies to reach the observatory. Due to something involving gravitational effects, only some space expands. In fact, the result is that any row or column that contains no galaxies should actually be twice as big. In the above example, 3 columns and 2 rows contain no galaxies. These rows and columns need to be twice as big, the result of cosmic expansion, therefore looking like this. Okay. Equipped with this expanded universe, the shortest path between every pair of galaxies can be found. It can help to assign every galaxy a unique number. Okay, so we numbered all of them. In these 9 galaxies, there are 36 pairs. Only count each pair once. Order within the pair doesn't matter. For each pair, find any shortest path between the 2 galaxies using only steps that move up, down, left, or right, exactly 1 spot at a time. The shortest path between 2 galaxies is allowed to pass through another galaxy. For example, here is one of the shortest paths between galaxies 5 and 9. You just do the little zigzag. Except this is just going to be the Manhattan distance. Like, we're not going to need to do any pathfinding if they want us to be able to walk through things and stuff, which is really nice. This path has length 9 because it takes a minimum of 9 steps to get from galaxy 5 to galaxy 9. The A locations marked here are the steps. Here are some other example shortest path lengths. In this example, after expanding the universe, the sum of the shortest path between all 36 pairs of galaxies is 374. Expand the universe, then find the length of the shortest path between every pair of galaxies. What is the sum of these lengths? Okay. So what do we got to do here? We've got to parse this into something. We got to parse this, and then we have to be able to expand rows and be able to expand columns. And I'm just thinking about how we're gonna do this, and I think it'll be okay. I think we can do it in the normal vec of vecs. So usually on these grid ones, I like parsing into a vec of vec. So like, columns and rows, 2D array style. And I was just thinking about if expanding was gonna cause any issues there, and I don't think so. So I think we're gonna do it that way. Yeah, I think that's what we're gonna do. So let's start off by copying the start example, and then let's make a new cargo binary. Cargo new. This is day 11, and this is expanding cosmic expansion. Cosmic expansion, and then we're gonna name this cosmic expansion. Cool. In here, we're gonna make a sample.input file where we can paste in that. Awesome. Okay. And let's go ahead and get started. So we're gonna want a function for part 1. Looks something like that. It is gonna end up giving us a U size probably, so that's perfect. And let's sample input part 1, debug sample input part 1. Awesome. So I think we want to parse this. Let's parse this into like a structure called galaxy. That just seems like a reasonable thing to do. So we're gonna have a struct called, oh wait, no, it's not galaxy. This is a universe or something. It's bigger than that. Yeah, we'll call it a universe or an image. A bunch of data and from the observatory. I don't know. We'll call it a universe. It sounds funner. Okay, so universe has, and I think it doesn't want to have any named things. It just has a vec of cells, I guess. I don't have a spacey word for that, so we'll go back to just normally computer sciencey ones for that. And let's just throw some derives on it that we know we're gonna want. Debug, no, debug and clone. Actually, we probably aren't even gonna need that, but that's okay. But then we need our struct for cell. And actually, maybe I actually probably don't even need to have a struct. It's probably just an enum where it's either empty or a galaxy. And then this one needs at least debug and clone, but this is also copy because it's just a simple enum. And maybe we want partial equals order, I don't know, or partial equals and equals. Okay, so let's go. I'm gonna go. Let's go from the top. That's what I usually do. Impl universe. We're gonna write a parse method. Function parse. Wow. Is that actually the right implementation, Copilot? Okay, so we're gonna take our input, break it into lines. For each of those lines, we're gonna map to characters. For each of those characters, we're gonna either have an empty thing or a galaxy. Wow, Copilot. You even got the characters right? That's a little weird. Wow, but it hallucinated putting a galaxy in the center. I don't know why it decided to do that. That's fun. And then this, I wanted to make a impulse cell function parse. Yep. Yeah, and it did that for me. Cool. So then I can just do cell parse to break that down just a little bit better. Yeah, that is basically though what I wanted to do, Copilot. So pretty cool. I think we can get rid of this because this collect's gonna know, and actually I can get rid of this one too, because since we're setting it in a universe, it knows it needs to be a vec. Yay, type inference. Okay, so that was actually really easy. Let universe, I don't want it to be mutable. Parse it, and then let's debug it just to check it out real quick. We'll do to do so this can compile. Usually I have a little... Oh, did I not put it in the workspace? I didn't put it in the workspace. Hey, Clueless11, I can give it a shot with looking at a Python error, but Python is definitely not a language I code in super often. But feel free to, put it in chat or something and I'll take a look. No, I didn't want to do that Copilot-y thing. I need to put this in here. We have a cargo workspace to have all of our cargo crates organized, and I just need to add it to the list so that cargo knows that it exists, basically. Whoa. I didn't realize that Copilot wrote a whole clear galaxy method. Or wait, what did Copilot... Copilot made a whole main function as well. That was pretty crazy, Copilot. Uh, cause... Wait, what? Oh, I misspelled this. That's where the typo was. I saw a typo and I just wasn't finding it, and that was confusing me. But there we go. I'm getting the error, attribute error, window demo has no attribute in TK. So Okay, let's see. I ran a code before with Windows demo and it ran okay. Obviously, in this new one, it won't work. Um, Yeah, I don't know if I can help with that, unfortunately. Here, let me see if I can get it onto this monitor, though. Object has no attribute TK. Yeah, this has something to do with the tkinter widget library. I'm assuming that's kind of what you're in, because that makes sense, I think. But no, I don't really know enough about this. But is it just that you need to import it or maybe install the package? But no, I'm sorry. I know that's probably not very helpful. I will get back to my puzzle. Sorry I couldn't be more helpful there though. I wish I could have been. This just doesn't need to be mutable. There we go. Okay, so it looks like we can parse this correctly. Nice. So now I want to find empty rows. Yeah, no problem. Oh, and thank you for the follow, Clueless. I appreciate it. Yeah, okay, so now I want to find empty rows and empty columns, and I think that one won't be too bad. So let's write an impl for that. So function empty or is row. Let's do is row empty. That gives me a specific row, and I return a Boolean. Yeah, that's exactly right. Copilot is column empty. Yep. At column, and this is at row, and then we check all of them. Wow, that was pretty nice. I like that implementation a lot, Copilot. So these aren't used yet, but that's okay because I want a function that does get empty rows and columns. I'm just gonna get them both together. Oh no, I guess let's just get them separately. It's easier to get them separately. Is row empty? Yeah, so I do it you wrote the method for me and it goes the opposite way, Copilot. It takes the index in. Map to the I, map I, collect, yeah. It's like kind of a funny way to write that, but we'll leave it like that. Function get, and I definitely could get empty rows and empty columns in one loop, but the code's so much nicer when I don't. So I think we're just gonna not. And because then like the return value, I like know which one to expand and everything. So function expand row. So this one takes a self and a row, and we're gonna return a new universe. Yep. So in our new universe, we're looking at the cells in it, and we do row immediately, which is the same as we did for row empty, so at least we're doing the same thing. And we insert at position 0 empty. Wait a sec. At row, we just insert. Yeah, so that's not exactly what we want to do. So I want to insert a new row at usize. Yeah, because if I found an empty row, I want to just add a whole new row. So what I want to do is do new universe dot 0 insert at row. Yeah, Copilot had it that time. A vec of empty. That's the length of that's the length of the universe. There we go. That is what I want. And since it's square, this doesn't need to be row, but it could be. That like just duplicates the exact row. Okay, cool. And then we can do function expand column. For, yeah, exactly. For row in the universe. So for each row, we can mutate through them and we insert at column one empty cell. So here, this is how we inserted a whole vec. And how we insert a whole column here is by looping. So we do it differently for each of these. So then I also can just write a function called expand that takes a universe and returns a new universe. And let it mutable, sure, it can be new universe, that's fine. We get the empty rows, we get the empty columns. For row in empty rows, we expand it. For column in empty columns, we expand it. Perfect, Copilot. Love it. Copilot is really nailing this one. Okay, so now we can expand it, and then we just need to find the pairs of, we need to find all the galaxies. So yep, let's just start there, I guess. Function galaxies. This is actually a really easy one. Galaxies. Yeah, that'll work. Galaxies from a universe, we get a vec of, let's just go usize. I usually make a position struct for this, but let's just do it with indexes at the moment. I think that'll work. Wow. So it wants to pull an I product, which I think is coming from itertools, which is pretty cool, but we're gonna do it just the slightly old-fashioned way. And let's do for row, I comma row in, so self dot zero iterator or ruminate. There we go. For I, and then cell, if cell equals a galaxy, we push it to the vector, and then yay, awesome. Okay, so that's all the galaxies. And then I need to like pair them up. So function galaxy pairs is a vec of the pairs. Let's see how Copilot did this one. Multiple methods are never used. Yeah, I know everything's not used. Okay, so we have a mutable thing of pairs. We go through the galaxies. For J, so this is for only when they're equal. Yeah, so this one isn't exactly what I want, but it's kind of close. So we want to loop through the galaxies. Because I think actually, let me read this again about the pairing up. There are 36 pairs. Only count each pair once. Order within the pairs doesn't matter. Yeah, okay. So we don't want to we want 1 and 9 in a pair and not 9 to 1 again, right? Because those are the same. So we're going to do this inner loop a little differently. So we're going to go through the galaxies in order, and then we're going to do another inner loop from I to I plus 1 to galaxies.length. Yeah, exactly. So then we're just going to loop from where we are, keep going forward. And that's going to make it so we don't do both sides of the pair. And then we don't have to do anything for the case where I equals J now, because we made that impossible. The loop variable J is only used to index galaxies. What? I don't really understand. The loop variable J is only used to index galaxies. Needless range loop. Oh, consider using an iterator. Iterate galaxies.iter skip. Oh, okay, cool. Wait, what does it want me to do? Oh, okay. For inner for pair. Yep, for pair in or match. How about galaxy match? That'll work. Galaxy match in galaxies.iter skip I+1. There we go. Yeah, that. Yeah, that's really interesting. I like that a lot. So instead of doing the indexing, now we're going to just make an iterator, skip the first however many, and then just loop through it, which is what we were doing before, but now we're doing it more like explicitly with iterators, and I like that. So now we have our pairs. So then sum of pairs or something. Sum of distances. For pairs, you get galaxy 1 and galaxy 2. Close, as you said. Yeah, that is a way to do that, but it's not the good way to do it. The better way to do it is x1.absdiff x2, which does exactly that for us. Computes the absolute difference between self and other. So then this is the same thing. y1.absdiff y2. Sum that up. And like that's fine, but I actually like would rather write this differently, I think. I would have written this as self.galaxy pairs dot into iter dot map galaxy 1 galaxy 2. Actually, let's just break this down right away into x's and y's. And then we have this plus y1 dot abdiff y2 sum. Oops. Didn't quite get the right number of parens here. I think that means, though, I forgot one there. There we go. Sum of distances. Okay, and then part 1 here is literally just let expanded. Actually, I think I can just do universe dot expand dot sum of distances. Run that. We get 388. I think that is right. That feels right. Oh, 374. Ooh, the sum of the shortest path between all of them is 374. And I got 388, so I'm 14 over. That's interesting. I wonder how many galaxies I got. Debug out universe.galaxies. How many do I have here? Cargo run. So we got 1, 2. I should have just counted them. 9. So we do have 9 of them. In these 9 galaxies, there are 36 pairs. Okay, so let me count the pairs. Galaxy pairs dot length 36. Yep. So why is my Manhattan distance wrong? That feels like it's that doesn't feel right. But it probably is. Copilot did it for me, so I'm gonna blame Copilot. X1, Y1, X2, Y2, absdiff, yep. Map it to that and sum it. Yeah, no, that's right. Iter skip a few. Skip I+1, yep. Pairs push, yeah. Huh. I really thought that one was just gonna be it right away. This path has length 9 because it takes a minimum of 9 steps to get from galaxy 5 to 9. Okay, so 5 is 0, 1, 0, 1, 2, 3, 4, 5, 6. So it's 1, 6. Let's write that down somewhere. 5 is 1, 6. And then 9 is 0, 1, 2, 3, 4. Oh, this isn't the expanded one. Oh, no, it is. 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11. Okay, so that goes to 4 plus 5 is equal to 9. Yeah, okay. So that's the Manhattan distance. That's the right math. But that means I'm even more confused, because then what's wrong here? Yeah, so when you find a galaxy, you do its I and J. And it really doesn't even matter if I mix them up, as long as I'm consistent about it. Yeah, I guess I should check. I guess my expansion is maybe wrong. I wonder if these are reversed. What if I make this column and I make this row? Different answer, 382. Still not the right answer though, which is interesting. And get empty rows is row empty. We get a row and we say, are they all that? Yeah, so then when I go to expand a row, that's the one where we can add a whole thing of empties in. Yep, that one makes sense. So then the column's the other one, which again makes sense. And insert does it at that position, shifts everything to the right, but that's actually exactly what I want. Oh, but I can't recursively expand without a like dealing with that. So I might need empty rows dot into iter dot enumerate. And then this is I comma row, where it's row plus I, because like it keeps moving. That's kind of hilarious. Empty columns dot into iter enumerate column plus I. 374. 374. Let's get our puzzle input. Nice. Leave. I like that. I'm proud of myself for figuring that out. I got stuck on day 10 and we haven't solved that yet, so it feels good to get past some stumbling blocks there. Okay. Let my input, let my part 1 answer, debug my part 1 answer, and we get biggish number. The right biggish number. Okay. Let's go to part 2, but let's make a commit. Actually, let's remove some debugs first. There we go. Day 11, part 1. The galaxies are much older and thus much farther apart than the researcher initially estimated. Now, instead of the expansion you did before, make each empty row or column 1,000,000 times larger. That is, each empty row should be replaced with 1,000,000 empty rows, and each empty column should be replaced with 1,000,000 empty columns. In the example above, if each empty row or column was merely 10 times larger, the sum of the shortest paths between every pair of galaxies would be 1030. If each empty row or galaxy were merely 100 times larger, the sum of the shortest paths between each pair of galaxies would be that. However, your universe will need to expand far beyond these values. Starting with the same initial image, expand the universe according to these new rules. Then find the length of the shortest path between every pair of galaxies. What is the sum of these lengths? Okay, we're going to have to restructure here Because basically I don't think going to a million by a million grid is gonna scale. And we don't need a lot of that information. There's really not a lot we need besides the list of galaxies. And the empty rows and columns. So I think we're gonna do this a bit differently. We're gonna go. So let's make a function part 2. Takes an input. There we go. It's not at all the right answer, but that's okay. Let sample part 2 answer debug sample part 2 answer. Okay. In the example above, if each empty row were merely 10 times larger, you'd get that. If each empty row or column were merely 100 times larger, you'd get that. So they're not even going to give us a 1 million times larger sample. That's kind of amazing. So it's actually, and then there's another number. So like, it's part 2 and then like expansion factor. Or something like that. I don't know. And then I can actually implement part 2 or part 1 as part 2 with expansion factor of like 2 or 1 or whatever. Is it 1 million times larger? Yeah, should be replaced with 1 million empty rows. Okay. Sample part 2 answer. Oh yeah, it's the small one. Got it. Yeah. Okay, so, and actually let's just go ahead and assert equals that, and it's not 30, it's this. 1030 though, it was close. Small, and then I guess I'll call this one large, just to call it something different. And that's with 100. You get this number. Awesome. Okay, so we have our universe. Let's let galaxies. Universe.galaxies. Awesome. So I'm gonna. The galaxies are just these pairs. So, and now I want let empty rows, let empty columns. So what I want to do is I want to apply transformations to the galaxies for the empty columns and empty rows. Because all I really need is their positions. So like for no. That's not it at all. So for the empty rows, and then like for G in galaxies.itermute, if the x coordinate is greater than or equal to the row, greater than or equal to row, greater than or equal to row plus 1, greater than or equal to row plus 1. Why row plus 1? That's what it wrote. And equal to. I guess I would have done greater than, because if we have a row and we're expanding it, it really is going to add 1 below it. I don't think it matters. But this is expansion factor. For each empty one, we add however many this is. And do I need this row plus I thing? Because I did, that's what the plus I is for. I'm coming back to it. I got a little lost there for a second. So the row plus I is what we did up top to account for it changing as we were going. Do I need that? I kind of do. I could make my galaxies a little more complicated. Like I could have a struct called galaxy that has original equals u size of u size, and then expanded equals this. And then let mutable galaxies is mapping into my new galaxy. Perfect. Where if g dot original dot 0 is greater than or equal to rho, no adding the I. I actually don't even think I'm going to need the I anymore. Because I think that's the only thing I was using it for. This is expanded 0 plus equals expansion factor. Oh, I just need to get rid of the enumerate. Okay, awesome. So for row and empty rows, if the original is greater than or equal to row, we expand it by expansion factor. And then we have to do for the same thing for column. So for column in empty columns, for the galaxies, if the y coordinate is greater than or equal to column, increase it by expansion factor. Awesome. Okay, so now we need to do let pairs. It's basically the same logic we have up top for that, but we're gonna do it again. Galaxies.iter enumerate for I and the galaxy. Called map flatten. Oh, I'm not sure if that's what I need to read it before I optimize it. Okay, enumerate map. Pairs is galaxies.iter skip. Yep. Push pairs. Yep. Try replacing map with flat map. Okay. Yep. That does make sense. And I want to replace this with galaxies.iter skip map collect. There we go. From the galaxies iter skip collect. Yep. Collect to some kind of vec. Collect to a vec, and now we have a vec of pairs. Perfect. We can really just do the summing now. That's pretty okay. Pairs dot into iter map. Yep, because it's the same map I did earlier. Nice. Think that is it. But we got the wrong answer. So this was supposed to be 1030 and I got 1112. Dang, that's unfortunate. And I guess that also means that well, let's do this. Assert equals, it wasn't 30. 374. Assert equals my part 1 answer and this one. Cool, we made it all the way to there. And then I kind of assume that it's gonna break if I do this, but let's find out. Open part 2 of input and the expansion factor of 1. Oh, wow. Okay, so it actually worked all the way up to the same one that it just failed on. That's really interesting. So using the same thing for part 1 actually works. Oh, did I do it too many times? I think I did. It's an off by 1 error. Yeah, because 1 plus 1 is the same as 1 and 2, because I have it be 1 here, right? I think that it needs to be multiplication, not addition. Okay, so where is that? In part 2, when I do expansion factor, I want to just add expansion factor minus 1 of them. And then when I define what part 1 is, the expansion factor is actually 2, because we want to multiply how many there are by 2. Yay! That was right. Okay. Yeah, I don't know if I like my naming here. And I don't. It doesn't like. I guess it's doubling the size of it. Yeah, so it doubles the size of it, and then it times it by 10, 1,000, and then a million. Okay. Yep, that makes sense. Okay, so that all of those ones were nice and easy. So my part two answer is, but it's not that. It's a million. Oh. Yeah, that can go there. Debug, my part two answer. Big number. Yay, there we go. Day 11, part two. Awesome. Let's push that up. And there we go. So that felt good after not solving day 10. Feels good to solve that one and wasn't too bad. I was able to figure out the change really quick from part one to part two. So in part one, we had actually parsed to, here, let me find the galaxy structure. We had parsed into this nice universe structure, sorry, which was a vector of cells. And then when we did the expanding, we like actually added in whole new rows and columns. But it turns out that that was fine on the small grid, but doesn't work on when you need to expand by factors of like a million. And all we really needed to know was the positions of the galaxies. So our part two answer just works off the positions, like the XY positions of them, and just does expanding by like changing their coordinates. And that is basically how it works. So then once we have the positions, we can find the Manhattan distance between the pairs. And that is all we needed to do for our answer. So we don't need to actually keep the a million by a million grid anywhere. We just need the positions, and then we can do the math for the Manhattan distance and sum it all up. And that was day 11 of Advent of Code. I'm going to get out of here, come back tomorrow for day 12. And in the meantime, I will see everyone online. Thanks, team. See you later. Bye.